Okay, to continue our discussion about modeling motion, I want to look at an interesting example. Let's say that we have a ball right here, and it's on a ramp, it's at the bottom of the ramp, and you give that ball a push back up the ramp. Notice that the top of the ramp, this position up here, is defined as the origin, x equals 0, and so the ball begins away from the origin, and it's traveling in the negative direction. It's going to the left, it's going back to the origin, its position is getting smaller. And you give it that initial velocity. So we say that its initial velocity, or its v0, is less than 0. There's some velocity that it has to start with because you've got to push it up the ramp. Why is it less than 0? Because it's negative. It's going back to the left. So here you can see my vector diagram that I've drawn for this. I show at time 0 the object starts at 10 meters in front of the origin, and it's going to the left. And I think that we can all agree and all understand that as this ball rolls up the hill, what's going to happen to its velocity? Is it going to have a constant velocity? No, it's being subjected to gravity, isn't it? As it goes up the hill, it's being lifted off the surface of the earth, and so gravity is going to be pulling it down, making the ball slow down. And so it is going to have an acceleration, getting more and more slow. Its velocity, in other words, will become less and less negative, a smaller velocity to the left. And so you can see that I have drawn my dots getting closer together, smaller vector arrows, until finally, right at the top, the ball's going to do what? It's going to stop and turn around and start rolling the other way, isn't it? That's what I've done here. When the ball reaches a position of x equals 0, I show it stopping. I've kind of broken the rule and drawn 2 dots here just so you can kind of see that, yeah, it is going to turn around. And then it's going to roll back in a positive direction with a positive velocity. And is that velocity going to be constant? No. This time what's it going to do? It's going to be speeding up. It's going to be speeding up as it goes to the right, as its position increases. So a larger and larger positive velocity. So you can see here I've drawn a larger and larger positive velocity. So you should be able to do this, to draw a vector diagram or motion map for complicated motion like this. Just think about everything that you're trying to show with your motion map. What is the velocity like? Is it slowing down or speeding up? Where is the ball starting? Where is it going to end up? Things like that. And we can also graph this motion. Okay, so you can see that I've replicated this scenario over here. Here's my simplified vector diagram, which we've already discussed. And now I want to show you what a position time graph might look like for this object. You should try to do this on your own and follow along with me. Predict what you think the position time graph would look like for this object. And this is just going to be a sketch. I'm not really worried about numbers right now. I'm more concerned that you can understand the shape of a position time graph for these accelerating objects. Remember, this object is indeed accelerating. It's slowing down as it goes to the left up the ramp, and then it's speeding up as it goes to the right as its position increases down the ramp. So let's think about this very carefully. At time 0 right here, where does the ball begin? It begins at a positive position above the origin. And then it's going to reach the origin. So I need to show it reaching the origin after some time. So I know that after some time it's going to come back to the origin. And should I draw a straight line there? No. What does a straight line on a position time graph represent? A straight line represents constant velocity, one slope. Remember, the slope of a position time graph is the velocity, or how fast it's going. It's not going at a constant velocity, it's slowing down. So I need a line that starts out with a large slope, with a large negative velocity, and ends with a very tiny negative velocity, ends with a very shallow slope. So I'm going to start my line with a very steep slope, end it with a very shallow slope. And I think that you can understand that it's going to be a curve like this, like 1/2 of a U. It's going to be an open down curve. This is just a sketch. I'm just worried about getting the shape correct. This shows that the object is slowing down in the negative direction. It's moving to the left and slowing down. Let's think about the other half of its journey as it goes back down the ramp. Now it is increasing its position. It's going to end back here at 10 meters. And what is this velocity like there? Well, its velocity is getting larger and larger, more and more, a larger and larger positive velocity. So I need to make a line that starts off shallow and ends up quite steep, going from a slow velocity to a large velocity, a curve like that. And so you can see that this really looks like a U. I know mine is kind of sloppy, but I think you can get the idea. The object started away from the origin at a positive position, and it slowed down. I have a curve that is getting more and more shallow, and then it reached the origin. Once it reached the origin, it changed direction, and it started getting faster and faster as it moved back in a positive direction, a larger and larger positive velocity. But now we're going to make things a little bit more complicated. Now we're going to introduce the idea of a velocity time graph. It is possible, just like we have graphed position on the y-axis, it is possible to graph velocity on the y-axis. So I'm going to make a velocity versus time graph for this object. I always recommend that you figure out a way to split up or break up the question or the scenario. And this, I think, lends itself to kind of being broken into right here. My line really should be symmetric. So let's look at this first part of the journey. Maybe I could label this part A of the curve. I'm going to have an A portion and a B portion so you can see what's going on over here. Now let's ask ourselves some questions about the velocity. Remember, I'm graphing the velocity over time on the A part of the curve. We can also refer back to our vector diagram if we need to. It started out with a large velocity and it ended up with a very small velocity. But we also know, and we also need to ask ourselves, what kind of velocity is it? Is it positive or negative? What do positive and negative mean for velocity? They mean direction. It's going to the left. Its position is getting smaller, so that's a negative velocity. It is a negative velocity that is getting less and less negative because it's getting smaller and smaller. So I need to start it out at time 0, having a large negative velocity, and then after some time it's going to have a velocity, a small negative velocity. And then what did it do here? What does it do when it gets to the top of the ramp? It stops for a brief instant in time as it changes direction. And so I'm going to have, for the purposes of this course, your velocity time graphs will always be straight lines. They're not going to be curves. I'm going to have a line just like this. And this represents part A of the object's motion when it's going up the ramp. It's going backwards, it's going to the left, so the velocity is negative everywhere for that part of the journey. And it's getting less and less negative because it's slowing down. And then it stops. The velocity reaches 0. Then the ball is going to do what? It's going to turn around and go back the other way. What kind of velocity is that? It's positive. So for part B, I need to have a line that's completely up here in this quadrant of the graph. A positive velocity. And what's happening to that velocity? It's getting more and more positive. The position line is getting more and more sloped, steeper and steeper. So I need a positive velocity that starts small and gets larger and larger and larger. And this is part B of the journey. Part A is down here, part B. And this is a velocity time graph. This is another graph that will also help me to illustrate changes in motion for accelerated motion. But there's another type of graph we could make. We could take this and we could turn it into, I'm going to do a small one here, I'm just sketching, an acceleration time graph. The acceleration of the object over time. Now, this is a little bit complicated. We'll get into gravity later. But think about it. This object is moving up above the Earth's surface, coming back down. Its acceleration should always be the same because what is accelerating it? Gravity, pulling it back to the Earth. So its acceleration will always be the same. So I should have a flat line for acceleration. In fact, for the purposes of this course, your acceleration is either going to be a straight line across or 0 if there is no acceleration. So let's think about acceleration, what acceleration is, what it means. Acceleration is the change in velocity over time, right? Acceleration equals delta v over t. How is the velocity changing over time? In other words, It's the slope of the velocity time graph, isn't it? My velocity time graph here is one line, one straight line. It's linear, and it's going up and to the right. So my acceleration time graph would look just like that. So here you can see my summary, and this is incredibly important. This is really the main idea, the biggest idea that we're trying to get you to understand in this whole unit of motion is representing motion graphically. This is a position time graph. It shows you how the position changes over time. The slope of a position time graph gives you the velocity, the change in position over time, the rise over the run. So a velocity time graph is just very simply going to be the graph of the slope of the position time graph as time goes on. This was a complicated example. We'll do a simpler one in a minute. But remember here in this example, for the first part of the motion, the velocity was negative and getting less negative. It was decreasing. It was slowing down in the negative direction. So I had a diagonal line that is getting less and less negative. Right here, the object stops, turns around, goes back down the hill, gets faster and faster. So I have a direction change. Remember, positive and negative in terms of velocity just tells you direction. So I have a positive slope in part B that's getting more and more positive, getting steeper and steeper. Because the velocity time graph is the slope of the position time graph line, and the slope is changing because it's curved, because there's acceleration. I know there's acceleration because the velocity values keep changing as time goes on. For part B, it's positive, getting more and more positive. The slope is getting steeper. So for part B, I have a positive value that's getting more and more positive. As time goes on, my velocity is getting more and more positive. So velocity is delta x over t, change in position over time. And the graph of that is just the graph of the slope of the position time graph. And notice that we're not doing any calculations, we're just making sketches. And then finally, an acceleration time graph. Remember that acceleration is the change in velocity over time. So an acceleration time graph is just going to be the slope of this graph, of the velocity time graph. This is a straight line. What do we know about straight lines? Straight lines follow the form y equals mx plus b. That m is the slope. It is one value, one number for a line. And so here, this is a straight line going up and to the right. My rise over run is always going to be positive, so my acceleration is some constant positive value, the slope of the velocity time graph.